his task.
Okay, so this actually seems to be the wrong order, but I hope you can read it there because we're short of time, so I'm not going to fuzz around with this display stuff now. So actually, most of the work was done by my student Tamas Bobat, who unfortunately is not here today. But a couple of you of the Maxeller guys, I guess, have already met him because he took the training there at Maxeller. We're of course very grateful to Maxeller to get all this support so Tamas can do his student project there. So the actual topic we were working on is to implement BLAS routines. Why do we do this? There have been around a lot of implementations with which the applications could be significantly accelerated using Maxeller's architecture. But of course, in order to further spread this in the community, we thought, why not implement a standard library with which users could get the benefits of the Maxeller architecture without having, or without putting too much effort into porting. And one of the standard routines in numerical simulations, of course, is BLAS. So another title which was coined by Maxeller is called BLAS. So I put both titles on here. Yeah, the idea was to implement this as a Maxeller library structure. And this can either be called from the max.j file from within Java. By the way, this is still an application for a Java compiler, isn't it? To compile the max.j stuff. Or from your C or C++. So both options should be possible depending on how the user is going to utilize this. Now the scope is to study the performance we can obtain with the Maxeller DFE compared to standard implementations like MKL, for example, or ACML if you prefer AMD on the x86 in the x86 world, and then create a BLAS library for future use. Is everyone familiar with the BLAS routines? More or less. So it's basically vector scalar additions, scalar products, matrix vector operations, and matrix operations. This is what's being delivered by a lot of libraries, like, for example, the MKL from Intel and other numerical libraries. So my students started with with BLAS 1 with a very simple implementation. And for large vectors, he got quite promising performance results. So the result on the Maxeller DFE was already a lot faster than, we have to admit, a vanilla implementation. This is what I showed in London a couple of weeks ago. So he compared it with an X50 650, 2.67 gigahertz Xeon CPU, but of course this was the non-optimized version. So a guy who works with Paul Kelly at Imperial in London, he said, why didn't you just compare it with the MKL implementation? Which is, of course, perfectly justified to ask this question. So Tamas did the comparison with the MKL implementation, and his first approach on the Maxeller architecture was still 1.5 times faster than the MKL implementation. And this, of course, is not yet very much optimized because he just started his student project. Here's some more experiments he did. He used different numbers of DFE vectors for doing this. So eventually he ran into some saturation here, which was because of the PCI bus saturation. And this brings us back to what Oscar mentioned: you better avoid moving data around. You better utilize the LMM and the FMM as much as you can, which will be done in the next step, when Tamas will continue after his holiday. Yeah, this is again this PCI bus saturation. And to conclude this, because I've only got 7 minutes, so this is going to be hard to finish by 5. I like to point out this is still work in progress. I'm pushing Thomas to continue now because he just returned from his holiday. And yeah, he already did the comparison against MKL. The factor was up to 1.5 simple implementation. So far, he's only done +1, which does show, I think, promising results. Next, there will be, of course, +2 and +3 as well. We already got some inquiries from colleagues in the academic world who would like to try this out. And future work could comprise avoiding data transfer, which I already mentioned. If you paid attention to Oscar's talk, you don't want to do this. And even for +1, this should give us an additional speed up, especially for large vectors or when concatenating these class options. If you just do a standard vector-vector operation, this is not, well, this is just to test the whole thing. But if you have very large amounts of data that you can compute in space, and if you concatenate several class operations, then we expect to get the real benefit of this architecture. So I already mentioned that, the data concatenation. And another issue is the accuracy. There was an issue which was due to the architecture where we could only calculate every 13th element of a vector, and then we have to do it 1, 13, 2, 14, and so on, which is because of the wiring of what's going on in the FPGA. And then Paul Kelly suggested something called K-hub summation, which Thomas already took a look at, and he thinks to obtain better accuracy with that as well. And that's it. I used to have questions here, but I think we're going to skip that. Thank you very much.
So thank you very much, Carsten. So
On time.
yes.